cloud. And it was supposed to be lecture 10, but I kind of never really did lecture 9. So, gonna trace back a little bit. All right, let's get started. Actually, even before I get started with lecture 9, I need to add one note for, let's do lecture. There's one thing that I need you to know for your homework that I didn't mention. So lecture 8.75. Just very, very briefly, because for the third problem of your homework, I need to say one extra thing. So third problem of homework 2. It mentions that you should use the shape functions in the parameter domain. So let me just say here, using shape functions in the parent domain the parent domain side. Let me just recap original shape functions. So if you remember what we did before, I had an element, and this could be a quadratic element, a linear element, it doesn't matter. So we had x1e, x2e, right? And then we had maybe some value u1e, u2e, and then we had the shape functions. We had n1e of x, and we had another shape function, and 2e of x. Right, so this was the original setup, and in that original setup, we defined the shape functions directly in terms of x. Shape function in terms of x. So for the second shape function, for example, I needed to be 0 at x equals x1e. So this was the first shape function, and then the other shape function was x minus x2e, x1e minus x2e. So these were the original shape functions that I defined, and you can see that they are directly in terms of x. And so given these shape functions, I could express my, so given these shape functions, I had UH of x equals the sum of the shape functions times the nodal values. That's what we did originally. So this is the original setup. Then what I did on last week, Monday, and then we just coded it on Wednesday, was that instead of working with things, functions in terms of x, maybe I can map the x into some other space, xi, between -1 and 1. And then I introduce this map. And in particular, that map that I introduced last time looked like this. So x1e plus x2e over 2 plus 1/2 xi x2e minus x1e. That's what it looked like for the linear linear isoparametric map. Right, so that given any value of psi, I could go and evaluate x. And that's all we did on Monday and Wednesday. So what I want to just tell you, because you need it for your homework, is that let's say that I want to interpolate a function. Again, given u1e and u2e, that we didn't do last time, but this is what I want to show you today. So we can use shape functions in the xi space. We don't need shape functions in terms of x. We can define the shape functions for the xi and do everything with functions in terms of xi. We never need to define functions with x. And the reason why is because we have a map already that maps from xi to x. Then we can also have a function for the shape functions in terms of xi and interpolate the u's with xi. So that's what I want to say today. So let me repeat that diagram. So we have the xi space and we have the x space. And then we originally are told that we have these two values, right? And so what I'm going to do is define the shape functions in the same way that I did it for the x, but I'm going to define them over the xi space. Let me call this n2 of xi and the other one n1 of xi. They are defined in the same way as before. So there's one advantage to do it with xi. And that advantage is that the ends of this element are always the same. So the shape functions will not change for a given element. Before, you can see that the shape functions depend on x1 and x2. They are still just functions of x, but they are parameterized by the beginning and end of the element. But for the parent element, it's always between -1 and 1. So this one is always xi minus 1 over -1 minus 1. So this one is always xi, my xi is pretty bad, but over -2, always. And the other one is xi minus -1, which is +1 over 2. So note that now the functions, now I have no functions in terms of x. All the functions that I have are functions of xi. But that's okay. I can use xi for everything. I can use xi to get the map from xi to x. I can use xi to get the interpolation of the u's. So use ni xi for everything. So that includes an alternative version of, it's the same, but I can represent x in terms of xi as an alternative version of the isoparametric map. I won't do it, but if you expand this out, so x equals the sum of the shape functions times the nodal values. If you actually expand that out, you will get the exact same thing that I had here. It's the exact same thing. It's the same map. It just looks slightly different, but it's the same thing. Used to interpolate U. So now we won't get UH is not going to be directly a function of X, it's going to be a function of Xi. So what is UH going to be? UH is going to be N1. This is similar to what we did before. But now the only difference is that the functions are functions of Xi instead of functions of X. And so here, note that because I don't have UH as a function of X, I cannot plot directly the function UH of X, but I have two functions. I have X as a function of Xi and I have U as a function of Xi. So if I wanted to plot, I think this is what I asked for in the problem 3. What I asked is plot UH as a function of X. And so you might think, okay, how do I do that? Because I don't have UH as a function of X. I only have UH as a function of Xi. And so what you need to notice here is that, okay, we have basically X as a function of Xi and U as a function of Xi. So we have an implicit representation for U. We don't have it directly. We don't have an explicit representation of U as a function of X, but we have both as a function of Xi. So that means that I can use Xi, let's say, I can generate a bunch of points between -1 and 1. And then I can go and evaluate both the X and the U. Eval X as a function of Xi. So that will give me some vector with all the X components that correspond to those Xi components. I can also evaluate all the U that correspond to that Xi. And then I just ask Python to plot the X and the U. So I don't need an explicit function for U as a function of X because I have both X as a function of Xi and U as a function of Xi. What I do is I just set an array of Xi's, 100 points or 20 points or however many points you want, and I evaluate independently both the X and the U, and then I just ask Python to plot them. This is the third problem of your homework. So I'll upload this to the finite element interpolation PDF. But any questions about this? I didn't get to. I should have done this on Wednesday, but. All right. If not, then let's go to the actual lecture. All right, so finally, what we will do today is we'll put everything together. So today, finally, we've already done this strong form to weak form. Your first two problems of homework 2 are basically strong form to weak form stuff. We have done this approximation of functions for the last 2 weeks. And then what we are going to do today is actually do this part. So we are going to use the weak form and use the approximation of functions with the finite element to get a discrete set of equations. The goal is to arrive to something like what we had before for the trusses. So if you remember, this is the weak form. The weak form is find the U such that it has some continuity requirement and such that it satisfies the essential boundary condition. And then this integral is 0 for all the W's that vanish whenever we have essential boundary condition. All right, and so we have for a given element, we have the two shape functions. Today I'm gonna do it with the X. I'm not gonna do it with the isoparametric map. And then on Wednesday, maybe I can show you how to do it with the isoparametric map. These two are equivalent. You can use the shape functions with xi, or you can use the shape functions with the x. The only reason to use the shape functions with the xi is because for integration, we only have the rules for the -1 to 1. But the formulation, the derivation that I'm gonna do today doesn't care if the shape functions are with xi or x. Yeah, so this is the matrix notation, but I'll rewrite it with the, so basically what we have is that for a given element, given the two values, so for a given element, I can interpolate, if I have the two values, I can interpolate UH of X equals some, again, I'm gonna do it today with the shape functions in terms of X. Similarly, if I had two of these W's, if I have some other W, I could also interpolate this in the same way. And then this we did maybe 2 weeks ago, that if you have this, then you also have the derivative. So du dh is just the sum of the derivatives of the shape functions with respect to x times the nodal value. And from here, you also get dw dx is also just the sum of the derivatives times the nodal values. This up top is just some matrix notation that the book uses. But it's nothing more than notation. We don't have to pay too much attention to that. It's just you don't think that that is any different. All that those four things in the slide are representing is these sums. It's just in a matrix format. Okay, so we have that, and we have our weak form. So let's just put it into the weak form. That's all we need to do. Let's just put this into the weak form. What does the weak form look like? It was the integral, and we're going to integrate only over an element. So well, let me write the full integral, and then I'll just do it for one element. So the full integral is AE du dx times dw dx d omega, and then I think it's minus, but this one has a minus. And then plus the integral of w times b, w times b, and then the last one is the boundary condition. So minus w at 0 of t equals 0. So this is just in the boundary. So that was the weak form. And then out of this is an integral over the entire domain. But for integrals, it doesn't matter. You don't have to do the integral with the entire domain. You can just do the integral in chunks. So for now, let's forget about boundary term. And worry about integrals over omega e. So this is no problem, right? So if you have an integral that is from 0 to 1, you can always do the integral by doing it first between 0 and 0.5, and then the 0.5 to 1, it doesn't matter. So we can do the integral in chunks. So if we do that, then only the terms that I care about are, I care about this term. So this is the integral over the element, and I care about this term. Note that because this is only part of the integral, I'm not making the whole thing equal 0. So this is no longer an equality, but I still need to be able to compute these integrals. So I'm just going to worry about how do I compute these integrals. So this is no longer an equation. So I cannot make this equal to anything, but I need to compute these things. But this is where I will plug in my discretization, right? So this is where I will use my discretization. So this one, instead of du dx, I am going to put whatever my discretization is, which is this, is the sum of the derivatives of the shape functions. And then the derivative of w with respect to x is just the sum of the derivatives of the shape functions times the nodal values. That's one. And the other one, again, instead of w, I am going to put what w is. W is the sum of the shape functions times the nodal values. Times b, which could be a function of x, d omega e. Again, I had my weak form, and then that's one thing that I had. And the other thing that I had was, how do I interpolate functions using finite elements? By having these shape functions, interpolating a function is just the sum of the shape functions times the nodal values, or the derivatives is the sum of the derivatives of the shape functions times the nodal values. So I just put that in. And here comes the magic. The magic is that the ui's and the wi's are just numbers. This is just a number. Oh, numbers. The only functions that I have here are the shape functions or the derivatives of the shape functions. So what do you think I can do if I have an integral and I have some numbers? What can I do with those numbers? I can take them out. Also, there's some sums, but these are linear operations. So the magic is that I can do a little bit of algebra to take numbers out of the integral. So what I'll end up with here, let me use I here and let me use J because otherwise it's going to be confusing. And here I'm going to use I. You will see that this is equivalent to having a sum over I and a sum over J of W. And I should use this J, and I'll do I for this one. The naming is irrelevant, but as long as they are called differently. Okay, so I'm going to end up with a sum over I and a sum over J of Wi times minus AE integral the other one, I'm going to end up with a sum over I of Wi times the integral of NIE x dx. Kind of looks like magic, but all I did was take out numbers out of an integral and rearrange things a little bit. So really nothing more than some algebra between that line at the top of the page now and the second, the bottom line. And if you're not familiar with what matrix and vector operations look like, this left term, this sum over I and sum over J, you should think of as some vector matrix vector multiplication. So this hides basically a vector matrix vector multiplication, and this hides a vector vector multiplication, a dot product basically. So I can rearrange things. Again, this is nothing more than rearranging things. And here, so for linear elements, for example, there's only two shape functions. So these I and J only go from 1 to 2. So what I end up with is W times this matrix, and the matrix is going to be, here is dn1 dx with dn1 dx. And then these are all just the 4 possible combinations. So this one is dn1 with dn2. This one is dn2 with dn1. And this one is dn2 with dn2. And this is nothing more than rearranging this as a matrix, well, vector matrix vector multiplication, but it's the same thing, it's the exact same thing that I had before. Whereas this other one, you can imagine it will end up being a vector as well, times another vector, and that other vector is just this one right here, but just either n is n1 or n is n2. So it's this one. But here is either n1 or n2. So hopefully now this looks a little bit more like the truss problems. This matrix right here, this is my stiffness matrix. And this right here is a force vector. Well, the force vector is new because we did have a stiffness matrix for the trusses, but we didn't have a force vector. We had a force vector, but they were all outside forces. But now we need to integrate something. Now, how do you compute that stiffness matrix? Well, you need to do the integrals. And here there's several options. You either do it analytically or you do it numerically. We're gonna do it numerically most of the times. But the key thing is that these are completely well defined because you know the shape functions, right? So you know if you want to expand that out, you can say, okay, n1 is x minus x1 over x2 minus x1. And then just replace the different shape functions. And then you'll end up with some ugly expression, but it's gonna be some function of x. And you can integrate that over the element. And you'll get a number. So actually, I can tell you this, just believe me, but there's nothing unknown about that stiffness matrix. I mean, it looks ugly because you need to do these integrals and you need to take these derivatives, but we know all the information. We know the shape functions, we know the derivatives. We can always compute that integral. And so what I can tell you is that if you use the linear element, then those integrals actually simplify quite a bit. And you end up with AE. Actually, the only thing that is left out of the integrals is the length of the element. And then you end up with the same as the truss element. That 1 over LE comes from the integral. Again, I'm not going to do it, but if you integrate for a given element, if you actually write down what the functions are, just to give you a little bit of an idea, n1 is a linear function. right? So the derivative of n1 is just a number, and actually it's just probably LE. And then the other derivative is also LE. And then when you do the integral, you should get a 1 over LE at some point. And then at the end, you end up with 1 over LE. Or it's the other way. So the derivative is 1 over LE, the derivative is 1 over LE, and when you integrate, you get the length of the element. So you end up with length over length over length, so you end up with just 1 over length. And same for the other ones, because the derivatives are just either 1 over the length or minus 1 over the length. The right-hand side is not as easy because the b function could be some function, so then I cannot really simplify. The n1 and the n2 are simple. They're just these linear functions of x. But the b is, who knows what that b looks like. So depending on what the b looks like, what the integral looks like. So that I cannot simplify now. But any questions up to this point? Again, just to put things in perspective, we had the weak form. We have some weak form, right, which involves some integrals. On the other hand, we had this way of interpolating functions by summing shape functions and other values. We put in the interpolation into the weak form, and then we integrate only over a given element. Because the nodal values are just numbers, we can take them out of the integral, and then the integrals should involve only things that have to do with the shape functions, which we know. So then they are computable. And if you arrange them in a matrix form, then you get this matrix with these integrals that, again, it might look daunting, but you have all the information, so you can actually compute those integrals. And that is the stiffness matrix. And then the integral that involves the loading bx ends up with an integral of the shape function times the bx, and that is called the force vector. And now that looks more similar to what we had for the truss problem. So now we are very, very close to the truss problem setup. Any questions? All right. So let's see what I wrote here. Again, if you check the book uses matrix notation all the way. So I'm not gonna expand it out. I would say if you want to check out what this looks like in the book, this b is a vector that has the derivatives of the shape functions. This n is another vector that has derivatives of shape functions. So it's just different notation if you want to go back to the book, but these are the same elements that I had before. Stiffness matrix, force vectors is the same, it's just compressed into just vector operations. I think that's about it. A note about this. I'll leave this for the end. Let me see. Okay, I'll leave this for the end. I'll do one more thing before I go to that one. All right, so at this point, we have for a given element, I haven't done the assembly, which is the last thing that I need to do is the assembly. So what we have up to now is that for any given element, For any element, we can get the vector of the W's. Then we can get the stiffness matrix. And we can get the vector of the U's. And we can also get the force vector. So again, the vector of the W's and the vector of the force. That's what we have right now, these two sets of equations, the stiffness matrix and this force vector. But this is for a single element. And like I said, this is not an equation, because this ignores the integral over the whole thing. This is, if you recall what I did here, this was an equation because this had both the boundary term and it also had the integral over the entire thing. When I did this, I said, okay, let me just do the integral for a given element. But now I actually want to do, how do I go back to the entire equation? This, we're going to use the exact same thing. There's multiple ways of phrasing this, but to do the assembly, we're going to use the same thing that we did for the trusses. So assembly is just like we did for the trusses. So consider, I'll do it with an example because maybe that's easier. Consider the mesh. Let's just do two elements because then I don't have to do that much. And let's say that this one is fixed. So two elements with nodes 1, 2, and 3. So the nodes, and this is x. So node 1 has coordinate 2. Node 2 has coordinate 1, and node 3 has coordinate 0. And then the elements, element 1 has nodes 3 and 2. And element 2 has nodes 2 and 1. So consider that mesh. Then my global system of equations is going to be like this. This is just like we did for the trusses. So for a given element, let's say element 1, I will have W1 of that element, W2 of that element. Then the K, I'm just going to use the fact that I know that the stiffness matrix for the linear is just 1 minus 1. K of 1. So this is AE over L. Maybe I'll do it with that. This is AE over length of the, so this is all of the first element. So the area of the first element, the Young's modulus of the first element, the length of the first element, times 1 minus 1 minus 1, 1. Again, this is because in reality, this is the integral, but I just know that for the linear elements, the integral ends up being just this. And so for the assembly, what matters is what are the nodes that make up this element. This element 1 is made of nodes 3 and 2. So I just put 3 and 2. Move this a little bit to the left. So here it looks just like we did for the, I'm going to have a big K matrix. I'm going to have a big W1, W2. Well, it's actually just three. There's only three nodes. So big. Well, big. This should be the size of the number of nodes. This is number of nodes times number of nodes. And then I'm going to end up multiply by U1, U2, U3. And so here, this is the same thing as we did. So this one goes to the 3, 3 entry. So here I'm going to get E1. And it also goes here. And then here it goes the minus. And then here also goes with a minus. And for the second element, I'm just going to copy paste this. Well, and maybe I should add, this is 1, 2, 3, 1, 2, 3. For the second element, this one is 2 and 1. So 2 and 1, 2 and 1. And this should be 2, 2, 2. So this one goes to here, but with a 2. And it goes here, and then maybe I need to move this a little bit. It goes there and then a minus. And then nothing here, nothing here. So again, this assembly process is just the exact same thing that we did for the trusses. Exact same thing. Also for the force vector. So for element 1, I'm going to end up with W1, W2. And for now, let me just call this F1A, F1B. And then for element 2, this is W1, W2 dot, let me call this F2A, F2B. Again, this I don't know exactly the value because this depends on my force function, but this is, I know this is 3, 2, and this is 2, 1. So my overall force vector will look like F here, F1A, and then here F1B plus F2A, and this one F2B. Again, just need to see which, this gets mapped to the third element here, and so on. And this is my overall force vector. Okay, last before we go. Okay, so I assemble the same way. Now I can actually do my let me do it like this. Now this is the weak form. with the discretization. Okay, we stop right there, and then I'll have to do the deal with boundary conditions on the next on Wednesday. Well, hopefully you see that the assembly process is the same. It really, the key thing is just how to get that stiffness matrix and that force vector. That's really the key. Okay, I'll see you on Wednesday.